Assalamualaikum and good day to all of you. We will actually proceed with more examples for this lecture, and at this time around let us look at example 8. Alright, a uniform rod of mass M is hinged at the bottom and O so that it can rotate in a vertical plane. So this one is O here, and the length of the rod is 1 meter. So the length is 1 meter. A force of 10 Newton is applied horizontally to the other end, making the rod stationary with an angle of 30 degrees with the horizontal. So we need to find the mass, the M. Okay, how do you do this? Okay, let us look at how to solve this. Okay, so before this, you know that you can apply the first condition and also the second condition. So you need to apply all those condition if it's needed for you, and at this time around we can actually use the second condition. So taking into consideration that the moment about O. Okay, so we take moment about O since the system is stationary. So sigma torque about O equals to 0. Alright, so when you draw the diagram, so you need to actually determine D1 and D2. Okay, so since D1 and D2 are the perpendicular, see, the perpendicular distance to the line of forces 10 Newton, okay, and mg also perpendicular, see. Alright, so this one, let's say we put it as D1, this one is D2. So you can apply 10, okay, this one, okay, 10 times D1. So since the force actually tend to make a rotation of counter clockwise direction, so it will be positive. So 10 D1 minus mg, this one, because the force here, okay, will actually tend to make a rotation to clockwise direction, so it will be negative mg d2 equals to 0. Alright, so after that you need to use your mathematical skills. Okay, so this one is 1 meter, as you know, so you can actually determine the D1 and D2 using your Pythagoras theorem, right? So 10 times D1, okay, this one is, of course, this is also the same angle, 30 degree, so D1 is 1 sine 30 degree, so you minus the mg d2, okay, this part d2. So since the center of gravity here, okay, we'll make sure that it will be divided into half, so 0.5 cos 30 degree, so equivalent to 0. Right, so you solve this. Okay, so you simplify the equation. So let's say mg times 0.5 cos 30 degree equals to 10 sine 30 degree. Okay, and you can rearrange the equation. So m is actually 10 sine 30 degree divided by 0.5 cos 30 degree times the g, which is 9.81. So press your calculator, 10 30 divide by 5 divide by 9.81. So you will get around 1.18 kg. Okay, let me check again. Divide by 5 cos 30 9.81. Yeah, will be around 1.18 kg. Right, so let us move on to the next question. Okay, don't climb the ladder, because when you look at the question, the diagram there, it's quite dangerous. Yeah, but never mind, we just use the term don't climb the ladder. So a uniform 10-meter long 50 Newton ladder rests against a smooth vertical wall, such as depicted in the figure here. Okay, so if the ladder is just on the verge of slipping when it makes a 50-degree angle with the ground, so this one, yeah, find the coefficient of static friction between the ladder and the ground. Okay, so first thing first, you need to draw a free body diagram. Okay, and then you must see what are the forces acting on the system. Alright, so this one is the normal force, and this part will be the frictional force. Okay, since the wall is actually touching with the ladder, so there's another force here, P. It's also actually normal force, since this one is a smooth wall. Okay, so if it's not smooth, it will be the other way, where we actually need to find the friction. But never mind, I will talk about that later. So of course, this is the 50 Newton. Okay, so at the base of the ladder, the ground exerts an upward normal, this one. Okay, this is normal force, and a force of static friction, this one, the F, acts to the right. Okay, the wall exerts the force P. Some books, they use Fn. Okay, right, so that makes some books, they use this one, let's say Fn2, or this one is Fn1, something like that. Okay, so it depends on you actually, right, as long as you know what are the forces that actually acting on that particular system. Okay, so the wall exerts the force P, okay, to the left. Okay, so this part to the left. So you must actually know that P is horizontal, okay, because the wall is smooth. Okay, if the wall is rough, let's say not smooth, an upward frictional force, okay, upward frictional force would be exerted on the ladder. Okay, so since the question stated very clearly that it's a smooth wall, so you don't have to consider the frictional force. All right, so what you should do is that we use the first condition. Okay, so you already know the forces. at x direction, which is the f minus p, which is equals to 0. Okay, and then let us look back. Yeah, this one is F, frictional force here. Yeah, this one minus this one, P, okay, will be equals to 0. Or it's also actually equivalent. That means the F is equivalent to the P. Okay, so that makes the first equation. Okay, and say this one is 1. And we look at the component y, fy. So the component y is the n, right? And then also the 50 Newton. So that makes n minus 50, right? So n minus 50 equals to 0. This one is the second one. So you know already that the n there is actually 50 Newton. Okay, they ask you to actually find the coefficient of static friction between the ladder and the ground. Okay, so we still need to use the frictional equation. So frictional force is actually mu times the n. So the mu will times 50 Newton. So you know that the F is actually equivalent to this one, right? The F equivalent to P. So that makes this mu S, okay, mu S times 50 Newton equivalent to P. Okay, so the second condition of equilibrium, okay, you need to apply to solve this problem. Okay, so take the talks about the axis through this one O at the bottom of the ladder there, see? Okay, so you know that D1 equals to 10 sine 50 degree, and the D2 is right 5 because it's divided into 2, right? So 5 0 cos 50 degree. So sigma torque about point O will be equals to 0. Okay, following the second condition. So now it will be easier for you to solve it. So P 10. Okay, P, this one will be positive, right? So P 10 sine 50 degree. Okay, since you are talking about D1, okay, minus 50. Okay, this one 50. Okay, so 50 times 5. Okay, cos 50 equals to 0. So now you can solve it. Get 50 times 5 cos 50 degree, okay, divide by 10 sine 50 degree. Okay, so you just use your calculator and you can solve this. 50 times 50 so you will get P around 20.97, so it's nearly to 21 Newton. Okay, so now you can substitute this, you can substitute P into this one, right? So the P to mu S 50 Newton, so mu S 50 Newton equals to P, so mu S equals to P over 50 Newton, so P is 21 divided by 50 Newton, so you get around 0.42. Okay, so let us look at example 10. Okay, so a ladder is leaned onto a smooth wall and remains stationary. So it's almost the same as the previous one, but we look at it at the part where you need to calculate the force exerted by the ladder on the wall, the force exerted by the ladder on the floor, the frictional force on the floor. Okay, so this is actually 3 meter. Okay, so 3 meter, the angle is 60 degree. Okay, so you can solve this, okay, by drawing the free body diagram first. Okay, so you know this one is, let's say, F1. Okay, this one is F3, and another one is F2. Okay, so it is the same as the force exerted by ladder on the wall. Alright, so this problem, since the wall is smooth, okay, since the wall is smooth, the only force on the ladder at the wall is the normal force, okay, which is the F1. Okay, the one that, okay, this one, right? So F1 is the normal force. Okay, it's the normal force. Okay, so taking talks about O. Okay, about O, this one. Okay, so you can actually calculate the force, right? So F1 3, okay, so this one is 3 meter, right? F1 3, okay, but of course you know that you need to use the triangle, right? So this one is 3 meter times the, okay, sine 60, because this one is 60 degree as well, so you can find this distance. Okay, so you will get times 3 sine 60 degree, right? And then you minus the, see, the mg, this one, right? mg. Okay, so the mg, center of gravity, is half. That makes mg times the 1.5, 3 divided by 2, right? And of course cos 60 degree. So this one cos 60 degree, okay, because you are actually, you know, need to find the distance here, okay. So it's cos at this time around, so cos 60 will be equals to 0, right? So you rearrange the equation, so f1 equals to mg 1.5 cos 60 degree divided by 3 sine 60 degree. So you know the mass of the ladder is 10, so you just plug in the value. 10 G is 9.81, 1.5 cos 60 degree divided by 3 sine 60. Okay, so use your calculator. 60 you will get around 28.32 Newton. Okay, so for part B, you need to find the F2 and F3. Okay, this one F2, F1 you already determined just now. So we use vertical force F3 minus the mg here. Okay, so F3 minus mg equals to 0. So you can get F3 equals to 10 times 9.81. So you will get 98.1 Newton. Okay, so for this one is the vertical part. Okay, this one is the vertical part. Look at the horizontal part. Okay, it's F1 and F2. Okay, so F1 minus F2, F1 here minus F2, okay, you get 0. So that makes F2 equals to 28.32 Newton. Okay, so force on the floor is equals to F2 square equals to F2 square plus F3 square. Okay, so F, then you set it F2 square, F3 square. Okay, so this is the force on the floor. So you will get 98.1, the F2, oops, sorry, F2 is 28.32. Okay, 28.32 square. So the F1, F3 is 98.1 square, and the square root, you get around, use your calculator, square plus 98.1 get around 102.11 Newton. So you can calculate the theta as well using tangent inverse of the y component divided by the x component. So the y component is f3, right? So f3 divided by f2, which is the x component. So you will get around 73.9 degree. Okay. What about the frictional force on the floor, the F2? So you know that frictional force is already determined, okay, which is the F2. You get 28.32. Okay, so we have completed our lecture for static equilibrium. So I have shown you examples on how to solve, okay, and we already discussed before from our previous lecture. So I really hope you guys can discuss among you and try to solve this problem together. I wish you all the best. Okay, thank you very much.